Hello, and thank you for choosing to watch my ISBA 2021 talk on a compositional approach to Bayesian computation. So in this short talk, I want to just give a quick introduction to some ideas of how to do Bayesian computation better. Okay, so what do I mean by that? So let's get started. For most non-trivial problems in Bayesian inference, we end up having to compute something, and that computation ends up being not completely trivial. And so very often we rely on computationally intensive methods such as MCMC or sequential Monte Carlo or ABC. Some kind of Monte Carlo method or some other computation intensive method. What I'm saying is certainly not specific to Monte Carlo algorithms at all, but they're a useful class of algorithms to have in mind. So if you're lucky, you might be able to get away with using some off-the-shelf package such as JAGS or STAN or PyMC3 or something like that, but very typically you will not be able to do that for some reason, either because you're developing new methodology or because the problem is too challenging for those off-the-shelf software solutions, and so you end up requiring some kind of custom implementation. And so to create that custom implementation, you first of all need to pick a programming language in which to implement that solution, and this is where all of the problems start, because all of the languages that are typically used for this problem are very old. Really, most of them date back to what we might call the dawn of the computing age, and are just not at all suitable for writing scalable and efficient algorithms for Bayesian computation. So in particular, many people in this audience will probably be familiar with interpreted dynamic languages such as R or Python or MATLAB. There are lots of problems with those languages, but in particular the obvious problem is that they're really too slow for any kind of computationally intensive method. So what tends to happen is that people end up implementing computation intensive algorithms in other languages, and the languages that are typically used are languages like C, C++, Java, or even still sometimes Fortran. Okay, but whilst these languages are indeed much faster than the likes of R or Python, they're actually even worse languages for implementing Bayesian computation. I mean, they really make your life extremely difficult. They make it very difficult to write correct code, to implement algorithms, to test algorithms, and to take advantage of modern computing hardware, such as multiple cores or processors. I'm not saying that it's not possible to use those languages to write efficient algorithms. Of course it is possible. You can do most things in most languages if you try hard enough, but these languages basically make your life as difficult as possible, and there's just no reason to do that. There are much better languages that will make your life much easier when it comes to developing Bayesian computation codes. Okay, so what's wrong with those languages? Well, there are lots of problems, but the fundamental one is that they're all very imperative programming languages. So what do we mean by that? We mean that they're very instructional. They're all about saying do this, do that, change this variable, etc. Okay, mimicking closely the way that computer processors, or at least early computer processors, operated. Okay, so it's easy to see how early programming languages were developed in that way, because they were simply producing a translation from this slightly higher level language down to assembly or machine code. But these days we really just don't have to work like that. We don't have to think like that. We don't have to use programming languages that were developed in that way. So in the decades that have happened since those languages were developed, there have been massive advances in computing science, in the understanding of programming languages, and of course there have been massive advances in computer hardware. So the computer hardware we have today looks very different to the computer hardware that was around at the time those ancient programming languages were developed. So today I'm emphasizing functional programming languages. Now, functional programming languages are not new, but there's been a big resurgence of interest in them in the last few years as people have come to realize that they just make it much easier to develop large, complex codes, scalable algorithms, and in particular, algorithms that are able to take advantage of modern computing hardware. There's a slightly different point, which is that there's also been a bit of a swing away from dynamically typed programming languages back to statically typed programming languages. And that's for multiple reasons also, partly because it allows you to develop more efficient code, which is a good thing, but also because it just allows you to write more correct code, because it helps you to trap lots of errors that otherwise might slip through, at least until runtime. So, what do we get from using these functional languages, and what do we really mean by a functional language anyway? So, functional languages, at the kind of most basic level, they really emphasize the use of immutable data, the use of pure referentially transparent functions, and higher order functions. And by that I mean functions that can accept other functions as arguments or return other functions as values. So by describing computation in terms of pure functions, you de-emphasize the imperative nature of the computation. So you move more towards describing the computations that you want to do, as opposed to exactly how it will be implemented, and that then gives the computer and the compiler a little bit more freedom to decide on good ways to do that computation, and that can be very useful. So in particular, by taking this approach, you get a much more modular and compositional framework for structuring your code, for composing models, composing data, composing computation, and that is really at the heart of why you get more scalable and testable software. So statically typed functional programming languages, and Haskell and Scala are good examples of them, they correspond closely to a mathematical model of computation called the simply typed lambda calculus. And the simply typed lambda calculus is one of the canonical examples of a mathematical structure called a Cartesian closed category. Okay? So this is what leads to the connection between functional programming and category theory. And that connection is very useful because what it allows us to do is to borrow lots of interesting and sometimes slightly mysterious ideas from category theory, bring them into functional programming, and use them to solve problems in a much neater and more elegant way than we would otherwise obviously be able to do in a pure functional programming language. So this is a very productive relationship between these two ways of thinking. Okay, so what do you get? Okay, so if you've got to learn a new language, a slightly new way of thinking about how to do programming, maybe even learn a little bit of category theory, what do you get in return? Well, the real killer feature of functional programming languages is they essentially solve concurrency, parallelism, and distribution for you. Okay, now it's a slight simplification, but to a first approximation, that's true. So what's that all about? Well, modern computing platforms, they feature processors with many cores, possibly many processors, and you really need to do parallel programming to exploit those properly. But parallel programming is notoriously difficult. And when you dig into it, most of the problems with parallel computing, the reason why it's hard, it all boil down to dealing with shared mutable state, right? Dealing carefully with shared mutable state, making sure that different threads or processors or computers all have a common understanding of some shared mutable state, is really at the heart of most problems with parallel computing. But in pure functional programming, state's not mutable, so any state that's shared is not mutable, so you don't have this shared mutable state problem at all, right? So 95% of the problems with parallel computing just disappear when you use a pure functional language. Okay, and so that then is a real selling point for functional languages. Parallelism and concurrency are so natural that it's often completely automatic, and you can often write code that's completely agnostic to whether or not it's being executed in serial or in parallel. That's a mere kind of implementation detail. So this is really one of the reasons why functional languages have taken off again in recent years. But in some ways, that's kind of missing the bigger picture. So the bigger picture is that these functional programming languages are just much more naturally modular and compositional and scalable. And easy parallelism and concurrency is one benefit of that increased compositionality, but it's by no means the only one. So it would be kind of bad to kind of think that was the only thing you get by using a functional programming language. No, that is just one of the benefits you get from working in this more compositional way. So as a Bayesian, what do you get? Well, here are just a few examples from Bayesian computation for how maybe doing things in a functional way makes things easier and better. Okay, so for example, you maybe heard of the MapReduce paradigm for computation. Well, that's a very simple kind of functional model of computation that's associated with functorial data collections, and that allows you to trivially parallelize lots of computations that you might do in a Bayesian algorithm. So for example, it would allow you to easily parallelize likelihood evaluations for a big data set. Okay, it will allow you to execute ABC algorithms in parallel. If you're doing something more sophisticated, like some kind of sequential Monte Carlo algorithm, it allows you to do those SMC steps in parallel. So parallel reweighting, parallel resampling, etc., all become very simple and natural in a functional language. If you've got something like a Gibbs sampler on a big conditional independence graph, that turns out to the execution of the Gibbs sampler turns out to be a so-called cobind comonadic operation. Okay, so there's a notion from category theory called a comonad, and you can use that comonadic structure in order to efficiently and elegantly implement Gibbs sampling algorithms on conditional independence graphs. If you're interested in doing some kind of probabilistic programming, as many of us are, it's very easy to develop probabilistic programming languages in functional programming languages using monads. Okay, so comonads are a nice way to think about conditional independence graphs, and monads are a nice way to think about probability distributions and composing probability distributions to make probabilistic programs. Also, I don't have time to get into this, but automatic differentiation algorithms on compute graphs is also very natural and elegant in functional languages, and that then facilitates any kind of gradient-based algorithm that you're interested in executing. Okay, so very short talk. To wrap up then, all of the languages that are commonly used for Bayesian computation actually, I would argue, are very poorly suited to the task. Functional programming languages, especially those that borrow ideas from category theory, are a really good foundation for scalable modeling and computation, and these ideas from category theory, such as functors, monads, and comonads, really allow us to improve the way we think about how to organize computation in a very productive way. Functional languages are really good for probabilistic and differentiable programming, and this definitely isn't about one particular favorite language, right? And it's definitely not about language syntax. It's not about whether braces are better than white space. It's not about whether, it's just not about syntax at all. It's about a class of languages, statically typed compiled functional programming languages with type inference and higher kind of type. If you've got a language that fits that bill, it will probably be an interesting and useful language for doing any kind of scalable computation, but Bayesian computation in particular. Okay, so this was really just a taster to get you interested in this topic. I've prepared a whole set of materials that explore this topic in more detail, including a link to a longer talk that I've given on this subject, where I unpack things in a bit more detail and give specific concrete examples of how to do things and why the functional approach is better, and what a monad is, etc. So please take a look at those materials if you think that there's anything interesting here at all. And like I say, there's lots of links to work by me and indeed lots of other people on this topic. Thank you very much for your attention.